Welcome back to the lectures. We move on to the last section of this, namely the review of elementary vibrational spectroscopy that was carried out over several lecture modules in this course. The important starting point for us was the simple harmonic oscillator model. And I recall that I had a fairly elaborate session on the quantum mechanics of the harmonic oscillator model. I gave you the energy level expressions as well as the wave functions for the harmonic oscillator. Now recall that the harmonic oscillator Hamiltonian is the kinetic energy to mu d square by dx square, and this being p square operator by 2 mu plus half m omega square x square, and this is nothing but half k x square, where k is the force constant and omega is the, okay, I am using mu, so let us use mu here, and omega is the angular frequency of the harmonic oscillator Therefore, and it is given by 2 pi nu, that is equal to omega. The relation between k and angular frequency is obvious from here, namely k is equal to mu omega square. Therefore, omega is k by mu and the frequency nu is 1 by, that is a square root here, 1 by 2 pi square root of k by mu. So, given the harmonic oscillator frequency from the experiment and knowing what the molecule is, and therefore we are able to calculate the mu, it is possible for us to calculate the force constant. Such exercises were given to you for different molecules, simple diatomic molecules, and I gave you the what is called the fundamental frequency. This is called the fundamental harmonic oscillator frequency. And the fundamental frequency is related to the force constant, that it is this proportional to the square root of the force constant. It is proportional to the inverse of the reduced mass. Therefore, if we have molecules such as Hd and H2, and we know that the force constant between the two hydrogens and the hydrogen and deuterium are approximately the same, then the reduced mass for these two species are different, the reduced masses are different, and therefore the harmonic oscillator frequencies will also be different. In fact, nu of isotope 1 divided by nu of isotope 2 is in very straightforward to show that it is the reduced mass of the isotope 2 divided by the reduced mass of the isotope 1. Such exercises were also given to you to give an idea that how by a very simple mass shift it is possible for the harmonic oscillator to have a slightly different frequency. And that is particularly important for isotopic species where the chemical nature, the force constant which determines the chemical association between the two atoms, does not change by much. Therefore, keeping the force constant, it is possible for us to calculate the shift in the harmonic oscillator frequencies and vice versa. I think such calculations were given. Now, the one important difference for harmonic oscillator from the microwave spectroscopy in terms of the absorption of radiation, infrared radiation in this case, is the fact that the dipole moment mu must change during the vibration. Okay. Therefore, molecules which have permanent dipole moment such as HCl, CO, then NO, H, Br, I mean all those molecules, During vibration they already have a non-zero dipole moment, and during vibration the dipole moments also change. It is a change in dipole moment during vibration which leads to vibrational energy absorption, and the vibrational states are all given by the expression as the eigenvalue for this Hamiltonian H psi n is equal to E n psi n, and E n is h bar omega n plus a half psi n. This omega is the same as that, the angular frequency. Therefore, you see that the harmonic oscillator has introduced a new quantum number n whose value starts from 0, 1, 2, etc. And even when n is 0, the harmonic oscillator still has what is called the 0 point energy, namely half h bar omega, and that is important. That is a quantum mechanical outcome. The application of quantum mechanics leads to this kind of prediction that there is a 0 point energy for the molecule even at 0 Kelvin. The harmonic oscillator energy levels are all equidistant, because the lowest energy level when n equal to 0 is half h bar omega, n equal to 1 is 3 halves h bar omega, and n equal to 2 is 5 halves h bar omega, and so on. Therefore, in the harmonic oscillator approximation there is no vibrational spectrum for a diatomic molecule, there is a single line, because the transitions between n and n plus 1 are the only allowed transitions leading to one line in the frequency, this to this or this to this or this to that, and so on. The transition between vibrational levels which differ by more than one is not possible within the harmonic oscillator framework, and one has to introduce what is known as the molecular unharmonicity. The vibrational motion is no longer harmonic, that is, the vibrational motion is no longer half k x squared, but there will be other terms like x cube and x to the power 4 and other types of terms, and these basically distort the vibrational motion from harmonic motion to anharmonic motion. We looked at the vibrational wave functions also. We wrote them as psi n, a constant root alpha x, as a normalization constant which depends on the quantum number n, an exponential minus alpha x square by 2, and the Hermite polynomial with the argument root alpha x, where alpha is square root of k mu by h bar square. So, k and mu are the parameters of the harmonic oscillator. Therefore, alpha is determined by the nature of the oscillator. This is the Planck's constant, and it is the same alpha that goes here, and alpha has the dimensions of 1 by length square. X is the displacement from equilibrium. Therefore, this is length square, alpha has 1 by L square as the dimension. So, root alpha x is dimensionless, and these Hermite polynomials were given to you as odd and even depending on whether n is odd or n is even. These formulas are given to you in the lecture notes, and therefore you might look at the wave functions, because the transition moment I between transition n and n prime, the initial state, let us write it as n double prime to the n prime, is given by the absolute square of the transition moment integral, namely psi n prime of x, I would say psi n prime of x here, psi n prime of x mu psi n double prime of x dx between minus infinity to plus infinity the absolute square, and mu being proportional as a displacement, the rate of change of mu has to change during the vibration, and that extent is given by the displacement itself. The displacement connects a wave function n prime and n double prime to give you non-zero values for this integral only if n prime is equal to n double prime plus or minus 1. For all the other values, the dipole moment does not lead to connecting a wave function n to a wave function n double prime, which is far away. It is required, the gap is required to be just 1 because of the fact that the dipole moment that we have is proportional to the displacement, and this is within the harmonic model. Therefore, the selection rule for harmonic oscillator is delta V is equal to plus or minus 1. This is not to be forgotten. So, this is the harmonic model that we had, and then there was a slight improvement from the harmonic model by considering unharmonicity in the form of a Morse oscillator. For the Morse oscillator, we wrote down the Morse potential proposed by Philip Morse first, namely the displacement, the potential as a function of the displacement is a constant times this functional form 1 minus e to the minus alpha x whole square. I would write this as x minus x e whole square, where v at the equilibrium distance x e is 0. You can see that right away. When x is equal to x e, this term is, the exponent is 0. Therefore, the exponential of 0 is 1, 1 minus 1 is 0, therefore the V of, so this is called the minimum in the potential. The Morse oscillator model allows us to consider molecular dissociation as a result of vibration, because if you plot the Morse oscillator potential as a function of the potential energy as a function of the displacement coordinate, this is x e and this is x, you would see that the potential is minimum, and then it rises until it reaches a plateau, and also it rises to a very steep value for x less than x e, because when x is less than x e, this is negative and there is a minus sign, therefore the exponential alpha becomes positive, keeps increasing as this becomes more negative. Therefore, you see that as x becomes more and more less and less than the equilibrium distance, when the atoms compress together very closely, you see that the potential rises very steeply, that is given. And you can also see the value of d as nothing but when x minus x e is very, very large, or x goes to infinity. Ideally, as a mathematical formula, when x goes to infinity, this whole exponential goes to 0, and therefore what you have is 1 whole square, and so you have d, and d is essentially the asymptotic value, and this d with respect to this value is called the dissociation energy, because at that extension of x, the molecule, the atoms do not come back, and therefore they are permanently separated from each other, and this is called the dissociation energy. The Morse oscillator also led to a very unique form of the energy expressions. You might recall the energy levels associated with the Morse oscillator were given by h bar omega e times a v plus a half minus I think I used only EB by HC to keep in mind that this is only a frequency factor, the centimeter inverse or a wave number, and then we have minus omega E XE V plus a half whole square. I think this is the expression I probably used in the lecture notes, and you can see that the vibrational quantum number V is 0, 1, 2, etc. Immediately what you see is that E naught is no longer half omega E, but it is half omega E minus 1 by 4 omega E XE because of this term, and E1 is 3 halves omega E minus 9 by 4 omega E XE, because this is 3 by 2 whole square, and likewise if I write E2, it is 5 by 2 omega E minus 25 by 4 omega E XE. The picture that the Morse oscillator immediately gives rise to from this kind of energy level expressions is the following. You might remember that the energy levels become closer to each other. So if I have to plot the lowest energy as the half omega e minus 1 by 4 omega e xe, the next energy level is not omega e, but there is also the difference between the two, which is 2. 9 by 4 minus 1 by 4 is 8 by 4, so there is a minus 2 omega e xe. So ideally, if you had to write this as half omega e and this as 3 by 2 omega e, it is no longer that, this is slightly lower than that, half omega e by this factor 1 by 4, and this is even lower. Therefore, you see that the Morse oscillator energy levels close in. The next energy level, if you look at E2, is closer to E1 than E1 is closer to E0, and likewise you can see that. So this is V equal to 0, V equal to 1, V equal to 2, 3 and 4. So what it means is that the gap between successive energy levels is no longer the same between any given pair. So you can see that this is not equal to that, this is not equal to that. Morse oscillator also allows in principle a jump from 0 to 2, and therefore what you see in vibrational spectra is that a central line corresponding to this, which is of a very large intensity, and then smaller lines which correspond to a slightly lower intensity, and a very weak line which is approximately at the twice. So if you write this as the nu E. So this is the first line corresponding to the difference between E0 and E1, which is omega E minus 2 xe omega E. And therefore, if we know two of these differences, we have two unknowns, namely omega E and xe. So with two differences we can calculate these unknowns, and therefore we can obtain the unharmonicity parameter for the Morse oscillator using the Morse model. And the nice thing about the Morse model is that the molecule for very large values in principle can dissociate. The harmonic model doesn't allow that. Please remember, the harmonic model is essentially that. No matter how far away the atom is and how high the potential energy is, the atom will always come back to its equilibrium and move around the equilibrium. That's the prediction of the harmonic model, which doesn't work in reality, of course, and therefore what you see as the Morse model as a very nice way of accommodating the actual molecular behavior. There are other models, there are other unharmonic models due to cubic unharmonicities, quartic unharmonicities, etc., and we will not in this particular course worry about those things, and I did not even introduce them. Those are important when you want to study the high resolution infrared spectroscopy of gas phase molecules of very, very, very highly resolved spectra. Then you need to worry about all those terms. Therefore, this is a precursor to understanding some of those things later. Now, we will just very quickly move on to the polyatomic vibrational motion and review what we have done. But before we do that, again please remember that for vibrational spectroscopy at the harmonic oscillator level, the selection rule is delta V is equal to plus minus 1, and it requires the dipole moment to change during the vibration. For the Morse oscillator, there is no dipole moment selection rule. All energy levels can be connected by the dipole moment operator, but the intensities of vibrational levels decreases very sharply as you go from V is equal to 0 to V is equal to 1 to V is equal to 2 and so on. Therefore, the lines become less intense as you go farther away, but there are lines, unlike that of a harmonic oscillator. Now, if we look at the polyatomic molecular systems for vibrational degrees of freedom, I told you immediately that an n atom molecule linear, there are 3n minus 5 normal vibrational modes, and you recall for linear molecule there are 2 rotational modes and there are 3 translational modes leading to a total of 3n. For nonlinear molecules, there are 3n minus 6 normal vibrational modes, 3 rotational degrees of freedom and 3 translational degrees of freedom, giving rise to a total of 3n degrees of freedom. And we were only looking at harmonic oscillator model for all the 3n minus 5 or 3n minus 6 degrees of freedom, and the harmonic oscillator model is obviously called the normal mode model in this particular case. And if I recall, I gave you a large number of animations, and the simple example of a carbon dioxide or ozone or water. These examples were given for specific reasons, namely in the case of ozone, all the 3 atoms which are vibrating about their equilibrium positions have the same mass. Therefore, the vibrational displacements of each one of the atom about its equilibrium is the same as the other. In the case of water molecule, these are lighter atoms and this is oxygen is heavier atom. Therefore, the vibrational amplitudes of the lighter atoms are slightly more in the vibrational period. That of the heavier atom is much less. And in the case of a linear molecule, you realize that there is one additional vibrational degree of freedom, and that led to what is called the doubly degenerate bending mode. For all linear molecules, one bending mode is OCO, bending in this plane, and the other bending mode is the carbon going behind the board and the oxygen coming in front. That is also a bending mode, and both of them have the same energy, and the bending mode frequencies are lower than the stretching mode frequencies. The stretching mode for carbon dioxide, there were 2 of them, a symmetric stretching, and this is called the symmetric stretching. And then there is this unsymmetric stretching or asymmetric stretching, in which one of the bonds is lengthened and the other is shortened. This was very special as well as the bending mode, because both of these induce a dipole moment in the molecule during the vibration. Therefore, the dipole moment changes from 0 here to a finite value and then goes back to 0 as the molecule completes one vibrational motion. This change in the dipole moment means that this degree of freedom and the bending degree of freedom are both infrared active. The symmetric stretching mode for carbon dioxide does not involve any change in the dipole moment from its original value of 0, because carbon is in the middle of both these oxygens. It is the center of mass, charge center as well as the mass center. Therefore, there is no dipole moment. So, when the molecule undergoes symmetric stretch, both the oxygens go away from the carbon at the same extent and then come back to the equilibrium position at the same time. Therefore, the symmetric stretching does not involve any change in dipole moment. It is not IR active. And this is true for a large number of linear molecules and molecules which have no dipole moment, such as the tetrahedral molecule CH4 or the planar triangular, with an atom in the middle of the triangle center, BH3 kind of molecule. Those are molecules which do not have any dipole moment for certain types of vibrational motions. But the fact that there are dipole moments introduced during other asymmetric stretches means that those modes are infrared detectable, and we see them in the infrared spectroscopy. Quite a number of such examples were given to you, and with this I think we sort of came to an end in telling you that vibrational spectroscopy at the level at which we have introduced, this was sufficient to understand. Most importantly, the relation between the force constant, the reduced mass, and the vibrational frequencies. The last lecture involved Raman spectroscopy, which was slightly different from all the other things that we did. Raman spectroscopy is a spectroscopy due to scattering of light, not due to absorption of light. So when light falls on a sample, which is something like this, and if you measure the light that is scattered in a perpendicular direction, the light that is scattered has frequencies which are modulated, which are changed from the original frequency of the light that irradiated the sample. And these changes are on either side of the frequency. They can be radiation with an increased frequency than the original one, and those are called the anti-stokes lines, and the radiation which has a frequency which is lower than the frequency of the original one, which is called the Stokes radiation, and the radiation of exactly the same frequency as the incident radiation was called Rayleigh frequency. And Raman spectroscopy, we introduced the concept of polarizability as, and the induced dipole moment as the reason for the observation of Raman spectra. The induced dipole moment is proportional to the externally applied field or the electromagnetic field that falls on the radiation, that falls on the substance, and therefore this is directly proportional to the magnitude, and the proportionality constant polarizability was introduced to you as a tensor of rank 2. Of course, we did not make use of that property in the lecture, the brief lecture that we had. We used the scalar property, and for Raman spectroscopy to be observed, it is important that molecules have one, polarizability for microwave region for rotational lines of Raman spectrum to be observed. Static polarizability is required. Therefore, when hydrogen, for example, undergoes rotation in the presence of an external electric field, the stretching, the separation of the hydrogen atoms leads to what is called the polarization of the two hydrogen atoms about the electric field. It introduces an alpha, and this alpha is static, and this static polarizability is responsible for the rotational Raman lines. Therefore, the presence of non-zero alpha means that even homonuclear diatomic molecules, N triple bond N, oxygen, all homonuclear diatomic molecules, and even molecules which do not otherwise have a dipole moment and cannot be detected using microwave spectroscopy can be actually detected using Raman spectroscopy, and the relation, and the reason for that is the presence of polarizability, that is the extent to which the molecule can be polarized in the presence of the external field. I also reminded you that the polarizability leads to a selection rule. Being a second rank tensor, even the static polarizability is like XX or XY or XZ, two quantities, two directional displacements, and therefore the selection rule for Raman spectroscopy is either 0 or plus minus 2 or microwave rotational Raman lines. In the case of microwave spectroscopy, we were only looking at the dipole moment of the molecule. Here, the induced dipole moment being proportional to the polarizability. It is the polarizability which is responsible for the rotational lines, and that being a second rank tensor leads to a selection rule of plus minus 2, and therefore rotational Raman lines are always seen between J and J plus or minus 2. So if you start from 0, the first line is 2, and you remember this is energy is 0, this is 6B, and therefore the first line has an energy of radiation. The radiation that is seen in the Raman spectrum has the characteristic frequency of 6B. The next one, if you look at say 1 to 3, this is 2B, and 3 is of course 12B, and the difference between the two is NB. Then you have 2 to 4B, 2 to 4, which is, this is J, these are all J, these are all J, and 2 to 4 is 6B to 20B, and therefore you have the next line 14B. Therefore, you see successive Raman lines come from the 6B, they are off by 4B to the next line 10B, and from 10B the next line is at 14B. Therefore, the Raman spectrum, if you look at it, the Rayleigh line, which does not have any frequency shift nu 0, is now shifted by the anti-stokes lines, namely nu 0 plus 6B as the first gap, and then it is nu 0 plus 4B. This is 10B. This is nu 0 plus 6B, and this is nu 0 plus 10B, and the gap between the two is 4B. This is 6B. And the same thing happens in the anti-stokes region when this is the anti-stokes region. The same thing happens in the Stokes region when essentially the energy is absorbed by the molecule, then that frequency is missing in the radiation, and you can see that it happens here. When energy is dumped by the molecules into the radiation from coming down in energy, that increases the radiation frequency on this side. So this is Stokes and this is anti-Stokes. This is Rayleigh line. Most important thing for Raman spectroscopy for us to remember was the fact that the polarizability is important, and in the case of rotational Raman lines, the static polarizability results in this radiation, in this kind of selection rule. For vibrational spectroscopy, it is again the change in the induced dipole moment, and correspondingly it is a change in the polarizability from the static polarizability during the vibration that was required, and therefore that did not change the selection rule for infrared Raman active lines. Raman active vibrational modes, the selection rules are the same as the infrared active selection rules, namely delta V is equal to plus minus 1. Okay. Therefore, vibrationally the only difference between the Raman spectroscopic lines and that of the infrared lines is that molecules which have a center of symmetry seem to choose mutually exclusive spectroscopies, either this or that. So molecules which have a center of symmetry have vibrational modes which are either Raman active or infrared active, but not both. But molecules which do not have a center of symmetry and which do have a permanent dipole moment are both Raman active and also IR active. Thus, for example, for water molecules we have Raman lines as well as infrared lines. For carbon dioxide we do not have. The Raman line is for the symmetric stretch and the infrared line is for the antisymmetric or the asymmetric stretch and the bending mode. So these are some of the elementary properties that come from the polarizability, the nature of polarizability and its change with respect to the vibrational motion that happens in the molecule. So with all of these elementary ideas now being told to you and hoping that you have followed some of these lectures, I wish you all the best, and I hope that you will continue the study of spectroscopy in a more profitable way in the future into other areas as well as into more advanced areas. I wish you all the best. Thank you.